Hello, everybody. Coming at you with a very quick video, just walking you through one example of a calorimetry calculation. In these calculations, what we're basically trying to do is we're trying to see how much energy is transferred into water and therefore being able to then identify what an unknown substance is. So I want to walk you guys through the process of first reading the question and organizing some of your information. We're going to have to do a calculation twice. As I'm looking at this, I'm realizing that I do not have the proper equation. So let's make sure we go ahead and review that. We're going to be looking at an equation where Q is equal to Cm delta T, where C is our specific heat, M is a mass, delta T is going to be a change in temperature, which is T final minus T initial. So in reading through this question, like I said in class, one of the biggest skills that we're going to have to be able to establish is being able to read the information and transfer it into our variable lists that we have here. Once we have all that sorted out, really all it comes down to is plugging in stuff into our equation right here, and then you're done. So let's go ahead and go through this process. You guys have a space where you can go ahead and copy this example down. And then you'll have this as a reference to be able to do a couple of examples after that. So I'm just going to read through this and I'm going to highlight and make sure to jot down the information that is relevant. So it first starts off by saying we have a piece of metal that has a mass of 59.05 grams. Now, because we are dealing with both metal and water here, we need to make sure that we have separate tables for each. And because, starting off right away, this is saying that we have a metal with a mass of 59.05 grams, I'm going to include that as my mass of my metal, 59.05 grams. So we've got that taken care of. As we continue to read, it says that 59.05 grams of metal was heated to an initial temperature of 100 degrees Celsius. So we're also given our initial temperature of our metal, which is 100 degrees Celsius. So I'm going to put that as my TI, or initial temp. And that's placed into 100 grams of water. So now we have a mass of our water, which is 100 grams. And that water had an initial temp of 23.7 degrees Celsius. So I'm going to include that as my initial temperature of the water. Then we took the metal and we combined it with the water. And when we combine those two things, the water and the metal reached equilibrium, meaning they reached a stable temperature. And that final temperature was reported to be 27.8 degrees Celsius. So what that means is that if they reach equilibrium, that means they both reach the same temperature. So if they both reach the same temperature, that would mean that our metal ended with a temperature of 27.8 degrees Celsius. And then that would mean that our water also finished with a temperature of 27.8 degrees Celsius. That's implied by the word equilibrium. They both ended at the same temperature. So then it's asking us, what is the specific heat of the metal? So what we're going to try to solve for here is our C. And then it also gives us a little bit of a tidbit of information here that the specific heat of water is 4.18 joules per gram degrees Celsius. So what it looks like here is, reading through the question, we've got a complete list of information that we're going to be able to use to plug into our equation right here to solve for the amount of heat that was absorbed by water. And then once we can figure that out, we know how much heat was released by the metal, and we can go ahead and solve for the C that is missing here. So let's first figure out how much heat was absorbed by the water. We're going to use Q equals Cm delta T. And now, instead of writing those letters, I'm just going to plug in the necessary values. My C for water is 4.18. My M for the water was 100 grams. My T final, remember, change in temperature is always T final minus T initial. So 27.8 minus 23.7. So all this really comes down to now is having a handy dandy calculator and being able to type in that information. So I'm just going to take 4.18. I'm just going to type this in as it reads in my work right here. We got 4.18 times 100. Then we're going to take 27.8 minus 23.7. Make sure everything's typed in there correctly. Looks like it is. And when I hit enter, what I find is that my Q of the water, or the energy absorbed by the water, was 1713.8, and our units for energy is joules. So what this value represents here is this represents the heat that was absorbed or gained by the water. Now, if we absorb a specific amount of energy, we know due to the law of conservation of energy, that energy that is gained must be lost by something else. And that energy that is lost is always going to be equal but opposite to the energy that was gained or absorbed. So if we had a positive 1713.8 joules of energy absorbed by the water, that means that our negative Q for the metal was equal to negative 1713.8 joules. Energy is neither created nor destroyed, it is conserved. So if this much energy was gained, the same amount of energy was lost, indicated by the negative sign for the loss and the positive sign for the gain. So now we have a Q for our second equation. We have an M and a delta T. We're going to be able to now solve for C. And I always like to add one extra step here. This is just going to help us out in the long run. So, and we're going to have to manipulate the equation anyway once we plug numbers in. So I like to manipulate that equation first. I want to try to make it so that C is by itself. So I'm going to do that by dividing by M delta T on both sides. That's going to cancel out M delta T, leaving us with the equation C equals Q over M delta T. Now I always like to do this step before I plug in numbers, because now I have a way that I have my work set up. So all I have to do is plug it into the calculator and get one answer. I'm not going to have to divide and then multiply. Not to do any of that. I can do it all in one step. So I'm going to go ahead and plug in all of my information now that I already have. Remember, we're trying to find C. Our Q was what we solved for on the first side. It's just a negative value now. So that's negative 1713.8. Then we're going to divide that by our mass, which was 59.05. Extend that out a little bit more. And then we're going to also include our delta T. Our final temperature, where the two substances reached equilibrium, was 27.8. And then we're going to subtract 100 from that, giving us a negative delta T, which is good because we're looking for that negative sign to cancel out the negative sign that's on top. So our answer that we end up getting should end up being positive, which is exactly what we're looking for. Everything that we have here should give us the specific heat of our metal. So let's go ahead and solve this. I'm going to plug in this number on the bottom first, so that way I can just easily divide the top from the bottom. I don't know, that's just how I like to do it. I'm sure you guys have a better way to do it, but it's all good. So 59.05 times 27.8 minus 100, that's going to give me the bottom of my equation. So now all I'm going to do is take my negative 1713.8 and then divide that by my answer. And what I find is that the specific heat capacity of this particular sample of metal, I'm going to round that to 3 decimal places, just because I like to have as many rounded digits as possible. 4.01, we'd round that 1 up to a 2. So what we would find is that the specific heat of this metal was 0.402 joules per gram degrees Celsius, which is the specific heat of our sample of metal. So if we were to extend this question a little bit further, we'd be able to find the identity of this metal, because we know that all substances have a unique specific heat, but this question is just asking for the specific heat we could use a reference table to determine what metal this is. But we're stopping there. So short, quick, to the point, just wanted to walk you guys through yet another example of how to solve something like this. You will then emulate this process on your own for 2 total examples. And we'll check in the next time I see you guys in class. But until then, keep being awesome. And I'll catch you guys next time. Goodbye.